Hi, everyone. My name is Michael Brett. I'm a principal specialist for quantum computing here at AWS. And today I'm excited to share with you one of the new technology areas we're investing in with a sneak peek into the future with quantum computing. Before we dive in, I want to talk you through what to expect in today's presentation. So first, I'll give an introduction to quantum computing itself and a quick overview of some of the fundamental concepts of this technology. Second, we'll take a look at Amazon Braket, our fully managed service in the cloud that enables you to develop with quantum computing hardware, simulators, and other tools that help you explore this new technology. And finally, I'll give a quick demo of our quantum computing environment, including PennyLane, a new machine learning algorithm environment that allows you to explore this new technology. So quantum computers are fundamentally different types of computers to what we're used to. If we look at the behavior of the very, very small down at the atomic scale, there's a different kind of physics that starts to emerge, quantum physics. So what if we could build a system that could control information at this physical level and do computational work? This different kind of physics allows us to do a different kind of math, and a different kind of math means a different kind of algorithm. And a different kind of algorithm means a totally different way to solve problems than what we're used to in the classical world. So let's take a look at what I mean by quantum information. Quantum bits, or qubits, are the fundamental units of information in quantum information processing, in much the same way that bits are the fundamental unit in classical processing. Classical bits can be in one of two possible states, either a 0 or a 1, like a light switch being turned on or off. Qubits, on the other hand, can access a much larger space in 3 dimensions. So think of a really fancy dimmer switch that can operate in any state between on or off, but also change the color of the light bulb. It can essentially operate in any point on the sphere. So it's helpful to think of this state between 0 and 1 as the superposition of a probability distribution for quantum information. And once a qubit is measured, its superposition will collapse into one of two states, either a 0 at the top of the sphere or a 1 at the bottom of the sphere. And so this forms the fundamental building block of quantum information. And by stringing many of these together and interoperating between multiple different qubits, we're able to do a different kind of computational work than we can do in a classical computer. Now, just as there are many different ways to realize a classical bit in classical hardware, say using different voltage levels or switches being on or off, there are also many different ways to realize a qubit in quantum computers. And I'll show you some examples of some quantum computers a little later on in this presentation. So now that we have a qubit, let's take a look at how we can manipulate this building block of quantum information physically. So just like in classical computing, where we can change the state of a bit, switching it on or off by applying some current or electromagnetic pulse. The same is true for quantum computing. So here on the screen, we have 2 qubits, and we can physically apply a current via a control circuit to change the information in that qubit. So you can see on the bottom row there with the qubit, we are applying an electromagnetic pulse with the yellow label, and that is manipulating the phase of the second qubit. By applying more qubit controls, we're able to change the information that's embedded inside this quantum informational building block and change its informational state, couple them together, and do computational work. So as programmers on classical computers, we don't really think about the physical circuitry that often, and the same is true for programming a quantum computer. We can instead represent the physical interaction with a series of gates. So think of these gates as like reading sheet music from right to left. So on the screen, we've got 2 qubits going through different changes in state from right to left. Each qubit is in a line, and as time progresses, we apply different gates in a different order, building up the circuit transformations to create an algorithm. In our case here on the screen, we've got 2 qubits, and we've performed 2 different kind of gates. The first is a Hadamard gate, which is a single qubit gate operation that has put the bottom qubit into a superposition. And then we've applied a CNOT gate, and this is a type of controlled gate where the rotation of our target qubit on the bottom is influenced by the rotation of the top qubit at the top. So in quantum computing, we have a diverse set of gates just like these that we can arrange over time and perform some really complicated algorithms. So with this unique and different kind of computational tool in our toolbox, well, what problems can we take on? There are many problems for which classical computers are really well suited, and the blue circle in the middle here represents those problems that are very easy for classical computers to solve. Quantum computing won't replace these at all, and you'll continue to use classical computers in the cloud, including CPUs and GPUs, to solve these kind of problems. The gray box around the outside represents all those really tough problems in the universe, including those problems described by complexity theorists as NP-complete problems. And these are just as tough for quantum computers as they are for classical. But there exists a set of problems in the middle, in the orange, that are really tough for classical computers, but highly efficient on quantum. And this is what we're able to take on now, what we're investigating here at AWS. So with quantum computing sitting alongside classical computers, we've got a new tool in the toolbox to do some really interesting things on some problems that were very difficult for classical computers to solve before. But how much better could these quantum computers be for classical computers on tough problems? Well, the truth is we don't really know yet, and this is the holy grail of quantum. We're building the systems at the moment. We're experimenting to see if we can find the solutions where a quantum computer can radically outperform a classical computer. There's a lot of space to explore too. There are many problems where a classical solution becomes increasingly more difficult over time as the problem size increases. So this is our call to action for you as developers. If you're interested in solving really tough business problems, as the time to solution increases exponentially as the problem size increases, quantum computing has the potential to unlock some really interesting ways to solve these problems and potentially solve them at a much faster pace than we're able to with classical computers today. So with the computers that we have access to today, the quantum computers, those with a limited number of qubits that are available, there are three application themes that are a really good space to explore quantum potential speed up at the moment. And what we're looking for is quantum commercial advantage. That is where a quantum computer is able to outperform a classical solution at the same price point that delivers value to you as customers. And so the three application themes that match the capabilities of quantum computers today are chemical simulation, machine learning, and optimization. And the common thread across all these themes is that they're underpinning inherently probabilistic nature of quantum computers to help solve these problems. The best applications for quantum computers today are the ones that can harness the unique properties of quantum information science and also accommodate the imprecise nature of the solutions that we get from these machines. So finding the kind of problems that rely on a probability distribution that could help speed up what we do in the classical compute space, that's a really good fit for quantum computing and an area that we're excited to explore. So with that background in quantum computing generally, let's take a look at what AWS is doing in quantum computing today. We have three pillars to our approach to quantum computing. First is Braket, a fully integrated AWS service that works in the cloud. It lets you design, test, and run quantum computing solutions in the cloud environment. Next, we have our Quantum Solutions Lab, a team of quantum computing experts who work here at AWS, and you can build applications with them, develop expertise, and do collaborative research together to investigate the potential of quantum computing applications. And finally, we've got the AWS Center for Quantum Computing. This is our deep research facility based at Caltech in California. We're in the process of building a brand new facility right now that will be populated with AWS scientists and engineers, sharing faculty and resources with Caltech to investigate some of the hardest problems in quantum information science, looking at hardware, software, algorithms, control systems, all of the building blocks necessary to overcome the tough technical challenges that will lead us to a commercial quantum advantage in the future. So let's take a closer look at Amazon Braket, our fully managed service in the cloud that makes it easy to get started with quantum computers. We provide a fully managed development environment based on Jupyter Notebooks that comes pre-configured with a suite of software tools, including the Amazon Braket Software Development Kit. The Braket SDK is a hardware-agnostic programming framework for quantum computers that allows you to access different quantum computing technologies with the same programming environment. This allows you to test and fine-tune algorithms, and we provide fully managed circuit simulators running on classical hardware that are parallelizable and cost-effective and always available. And most importantly, we provide access to on-demand, secure range of quantum computers in the cloud today. So let's take a look at the Braket architecture diagram. In the center of the diagram here, we've got Amazon Braket, which sits within the AWS cloud. On the right-hand side, this connects into all of the support services that you're used to from AWS, including CloudWatch for notifications, S3 for storage of results, and all of the standard identity management security provisions that AWS can provide. On the left-hand side, 3 different ways for users to access Braket. We've got the managed notebooks within the console environment. We've got a software development kit that you can download and run locally in your favorite developer environment. And then we've got a user interface through the Amazon Braket console, which gives you access to a range of information about the computers that we have available today. In the very center of the diagram, the managed simulators that run on AWS classical infrastructure that allow you to test the algorithms that you've developed in a scalable, low-cost way before deploying those algorithms to quantum computing hardware. Then finally, at the bottom of the diagram, we access 3 different quantum computing systems. So today, we have access to quantum computers from Rigetti, IonQ, and D-Wave. These 3 different quantum computing platforms represent 3 different modalities of quantum compute. So from D-Wave, we've got access to quantum annealing hardware. IonQ represents ion traps, and superconducting qubits from Rigetti. In the fullness of time, you can expect that we'll be adding support to other hardware systems and also increasing the depth of access to the platforms that we have access to today, allowing developers to exercise more control over the qubits that they have access to. And most importantly, with Amazon Braket, we follow the principles of cloud pricing. So you only pay for what you use with the hardware today. And without any upfront commitment. So you can just open your Amazon AWS console and get started in this environment. So for any hardware system, essentially the price to run any particular algorithm is just 30 cents to send across to a quantum computing system. So you develop an algorithm within the Jupyter Notebook console environment, test that algorithm on the fully managed hardware on the classical systems, and then you can send that algorithm across to our quantum computing hardware for just 30 cents to get a solution to that particular problem. We also have our simulator environments running on classical hardware in the AWS environment, and we offer 3 different managed simulators today. The first is our state vector simulator, which allows you to run idealized quantum circuits running on CPUs up to about 34 qubits. We launched in December a tensor network simulator that runs on GPUs, and this allows you to run some specialized graph environments up to about 50 qubits. And just in the last couple of weeks, we've launched a new simulator that's a noise simulator that represents the kind of quantum computing hardware that we have access to today. So you can test your algorithm on the idealized simulators with SV1, and then move across to the noisy simulators with DM1 and test circuits up to about 17 qubits in that environment. We've also been adding more and more libraries to the Amazon Braket SDK over time. So at reInvent in December, we introduced PennyLane. PennyLane is an open source software library that brings machine learning tools to quantum computing. And PennyLane has pioneered the idea of quantum differentiable programming by generalizing these machine learning concepts and applying them to quantum computing. And more than that, it allows you to use familiar machine learning libraries such as PyTorch and TensorFlow to program your quantum algorithms and make it easy and intuitive to get started with hybrid quantum computing. PennyLane comes pre-installed with Amazon Braket notebooks, and we have a number of tutorials to get you started, providing you access to application libraries for chemistry, optimization, and machine learning. And most importantly, PennyLane on Amazon Braket is optimized to allow you to train up to 10 times faster when you use the Amazon Braket simulators for their ability to run parallelized circuits. So now we're going to switch over to the Braket console, and I'll give you a quick tour of the console and an introduction to some of the PennyLane notebooks that we use as a demo of this environment. So we'll switch over there right now. So here we are in the AWS Management Console. This is the standard console environment for all AWS services. You can see all of the services listed here, including compute, containers, storage, and this new section called Quantum Technologies, which includes Amazon Braket, our quantum computing service. I use Braket all the time, so it sits up here in my recently visited services. But you can also search for it in the search bar, and it'll pop up right at the top there. So let's click through to Braket. This is now launching the Braket specific service console. It'll take a couple of seconds to load. You can see that we're in the region US West 1. And what it's listing here is all the devices that are available on Braket. So we've got the two D-Wave machines, IonQ and Rigetti, and then the simulator systems down the bottom here. If you click on any one of these tiles for a quantum computing hardware platform, so for example here with the Rigetti Aspen 9, it's giving us some more information about the Rigetti system, its availability during the day, the device address, the region that it's in, and the cost basis for that. You'll see here the topology of the Rigetti system and then some calibration information for that. We look at a different device instead. So for example, the IonQ platform. You see it's in a different region in US West 1. It's got a all-to-all connectivity graph shown here with 11 qubits and a range of calibration information there. And so this environment allows users to explore the different quantum hardware technologies, learn a little bit about the best practice and the differences between them. And then also here on the simulator side, very similar kind of setup for each of the simulators. There's a device address, availability in all the regions that our hardware is available in, and some information in the documents about connecting to those simulators. So with the Braket environment, you can write your application and then target all of these different solvers and compare for yourself what works best for your particular application. So let's go look at some applications in the notebook environment. So I've clicked through to the notebooks. I've already set them up, but if you came to Braket for the first time, you create a new notebook instance by clicking the orange button here in the top right. So if we click through to the Jupyter notebook environment, these are the example notebooks that come standard with Amazon Braket. So as soon as you instantiate a new set of notebooks, you'll have all of these available to you. And there's a whole range of example notebooks here to learn and explore and get the building blocks of quantum computing so that you can develop your own application. So let's look at one in particular. Just getting started here. This is a Hello World level application to prepare a entangled belt state with 2 qubits, which we can then run on a local simulator and obtain the results. So if we click through this particular application, we're bringing in the libraries that we need for the program. We're building a circuit. You can see this circuit needs a Hadamard gate on qubit 0 and a controlled NOT gate using qubit 0 and qubit 1, which is exactly the circuit that we defined at the very beginning of the presentation today with those 2 qubits. Then we'll run this particular service on the local simulator. We'll be doing this 1,000 times, obtaining the results, and then we'll plot these results here on the screen. We would expect that for sampling from a entangled belt circuit that we'd have around a 50-50 distribution, and that's exactly what is being shown here. So 1,000 shots through the platform, getting about 500 results each for bitstring 11 and bitstring 00, which is what we expect. So that's a really simple Hello World application. If we want to look at something a little bit more complex, let's go to the PennyLane machine learning library and pick this graph optimization problem using QAOA. So QAOA, or Quantum Approximate Optimization Algorithm, is an algorithm that's really well suited to finding the lowest energy state for complex multivariable optimization. And we can apply that to a graph optimization problem where we're looking at finding different subsets of complex graphs. This is really well suited to quantum computing because Graph problems have strong links to practical use cases in logistics and social networks and scheduling, and can often be really hard to solve for classical computers. So if we click through this, we're setting up a graph here. You can see that this is the 6-noded graph. It's not fully connected as a graph, and what we want to do is find the maximum size subgroup of this graph that is fully connected. Now we can visually see that it's these 4 qubits over here on the right-hand side being fully connected. But let's see what the quantum computer can do. So this program now sets up the QAOA algorithm. There's a complex set of quantum gates that play here. I won't go through the details on those, but suffice to say there's two Hamiltonians that we need to set up, which are energy functions, and then 2 different parameters that we need to iterate through and find the lowest possible energy state by combining classical optimization function, which we'll use Penny Lane for, and then bracket on the quantum computers. So we're setting up the graph here, and then setting up the particular algorithm, which we can pass to the solvers. The number of layers in our QAO algorithm is a trade-off between performance and quality of solution. We're going to select 4 because that's quite tractable. You'll see here that we're passing from our quantum machine learning library to the device the set of qubits that will represent this QAOA algorithm. And then we'll be using a gradient descent optimizer on a classical system to find a set of input parameters that can go into the Hamiltonians. So this will take a few seconds to run now as we iterate through and find different elements of the cost function. So we're sampling here from the gradient descent optimizer, and then we'll pass these across to the quantum system itself. We've set up the quantum simulator to run 100,000 shots with a variety of different parameters that we're passing into that as essentially seeds. So that's run already, and then we'll display the results here. Here you're seeing we're getting a probability distribution of all the possible results from the subgraph, and you can see that this particular one, 101110, is the most likely of the probability distributions to give us the maximum size click. And so let's graph that up and see if it corresponds to our expected output, which is these 4 here connected, which is what we visually saw. So that's using Penny Lane, our quantum computing simulator, to look at a fairly simple graph optimization problem. But this is where you come in. We can now scale this up and apply it to much larger graphs, which are more complex interconnectivity, and pass that through different quantum hardware platforms. So we'll leave that to you as a challenge following this presentation to play around with graph optimization with QAOA. So now we'll head back to the presentation. So that was the demo of quantum machine learning using Penny Lane in Amazon Braket. And recapping what we have with Amazon Braket, it's a hardware-agnostic quantum computing platform providing access to a range of simulators and quantum hardware technology. We've got end-to-end integration with the other AWS cloud services, so you can combine them into really interesting solutions applicable to your business. We have scalable circuit simulators in the AWS cloud, and we're following the pricing principles of the cloud. Only pay for what you use, and no upfront commitment to get started with quantum computing. So from today's presentation, the key takeaways. Quantum computing is a fundamentally different approach to solving hard computational problems. Braket is available today in the cloud to enable you to start exploring quantum computing, and customers and partners, like our friends at the Penny Lane open source community, are building tools to help you integrate quantum computing into your existing workloads. So thank you very much for the presentation today. I hope you've learned something about quantum computing, and of course, you've also joined the AWS Summit to learn And you can keep the learning going after the summit with IoT resources from our AWS Training and Certification. We offer over 25 free digital courses on demand so you can learn wherever and whenever suits you on your schedule. So for more information about our IoT curriculum, visit our learning library at aws.training. So thanks for joining us today. I hope you enjoyed this presentation on quantum computing.